Okay, we're now going to take a look at another important example of diffraction. This time, instead of a long, narrow strip of opening, I have a circular opening. So imagine light coming in, everything else is blocked except a circular opening of diameter d. This is an important special case because oftentimes light does go through a circular opening, such as the case of a lens, or even the human eye is a circular opening. Okay, now the details of the analysis contains math that's a little bit beyond our reach because you're not going to get something like a sinc function, which is elementary. You're going to get a special function. Okay, so we're not going to deal with that, but qualitatively, we can still understand what's going on. You know, when light comes in, if I draw an axis of symmetry from the center of the circular opening of diameter d to the center of the screen, then you know, just like the case of a single slit, you're going to have a broad central peak. It's broad and it's bright. Okay, and you're going to have some side peaks as usual. But because of the symmetry of the problem, everything should be symmetrical about the axis if you rotate about it because the opening is circular. So instead of long stripes of alternating bright and dark stripes, we are going to have rings. Okay, we're going to have circular rings. Here at the center, there's a bright spot of a certain diameter, and then you're going to encounter the first minimum at a certain radius. Okay, first minimum, and there is a second minimum, a third minimum, and so on. And just like the case of diffraction for single slit, the central peak is the tallest. Okay, most of the light is concentrated at a central peak. Now, after detailed analysis, you can actually find this function. Okay, find the function of intensity as a function of the angle theta. And this function turns out to be a special function, as I said, and it's named after the person who discovered it, and it's called an Airy function, A-I-R-Y, the Airy function. It's named after Danish astronomer Airy. And there is a reason why it was first discovered by an astronomer. Because, you know, when it comes to astronomical observation, we have to use a telescope, right? And the telescopes have circular openings, right? It's basically a system of lenses. And when you peek deep into the sky, you see a lot of stars. Sometimes the stars are very close to each other. In other words, the angular resolution of the telescope becomes very important. You got one star here and another star very close to it. Will your camera or will your telescope be able to tell them apart? In other words, you can tell that these are two different stars instead of one. Well, we can take a look at what kind of limit in the resolution power of a lens will the diffraction pattern impose. Okay, now suppose I have a beam of parallel light coming in. Okay, parallel to the optical axis. They come in, and after going through the circular opening, they're gonna produce a pattern like this. The bright spot in the middle, the circular spot in the middle, is called the Airy spot. Okay, it's called the Airy spot. It contains over 80% of the intensity of light coming through this circular opening. Now, obviously, the size of the Airy spot is very important because if the Airy spot is bigger, then if I got another beam of light at a slightly different angle, it's going to carry its own Airy spot. And these two Airy spots could overlap or get too close to each other. You cannot tell them apart anymore. So if you want a better resolution from the camera, from the lens, you want to make sure the Airy spot has smaller diameter or smaller angle, okay, extended from the lens itself. So what is the angular size of the Airy spot? And that is from the first minimum, okay, you know, it's the edge of the Airy spot to the center. You know, you can find this angle, right? You find this angle. We call this theta minimum. Okay, we call this theta minimum. What is that equal to? Well, let's see here. In the case of a single slit diffraction, this corresponds to the edge of the central diffraction peak, and we know how to calculate that. The answer was sine theta. Okay, was sine theta equals what? Lambda over a. Remember that? That was the first minimum. Sine theta equals lambda over a. What's a? A was the width of the slit. Okay, the width of the slit. Now, of course, I must replace the width of the slit with the diameter of the circular opening. So replace with d. Okay, replace with d. Do I get sine theta equals lambda over d? Well, almost. But you see, the geometry is different. This time I have to look at circular opening instead of a long strip. So therefore, the answer will be slightly different, but not that much different. Okay, the answer turns out to be sine theta equals, instead of lambda over d, there is a small constant in front of it, and that constant equals 1.22. Okay, so I have sine theta for this angle equals 1.22 lambda over d. Okay, 1.22 lambda over d. And in most cases, d is much greater than lambda. For most cases of practical importance, because we have to use a lens, right? Like a camera or a telescope. These lenses, we're looking at size of diameter of the size of centimeters or above, and therefore d is of the order of several centimeters or greater. Lambda, on the other hand, for visible light is about a half of micron. So indeed, lambda over d is far less than 1, and therefore theta is very small, so I can replace sine theta with theta itself. So I have roughly, I have theta minimum instead of sine theta minimum is roughly 1.22 lambda over d, and the order of magnitude is just about lambda over d, the same as the case of a single slit, except d now replaces the width a. Okay, so you see, in order to have better resolution, I would have one of these two things happening. One is I use a smaller, shorter wavelength, okay, and the other is I make the opening size greater. I use a bigger lens, okay. So that's one advantage of a bigger lens, because you get sharper images, you get better resolution. Of course, there is another obvious advantage, is that more light can go through, so the image will be brighter as well. So not only is it brighter, but also it has better resolution. Okay, now we can use this expression, theta minimum equals lambda over d, to look at what is the minimum angular separation between two remote stars, such that I can barely tell them apart after they go through this lens. Okay, imagine there is one star casting the beam this way, another star casting the beam that way. There is an angle between them. How small can this angle get such that I can still barely tell them apart? Well, this star will produce an airy spot like this, right? Which has its edge right here. Now another one coming that way, it's going to produce an airy spot centered here, right? Now we're going to use what's called Rayleigh criterion. Rayleigh criterion. The Rayleigh criterion was first proposed by Rayleigh, a British physicist. He proposed that in order for these two stars to appear as two different stars, the minimum angular separation between them would be such that the edge of one airy spot, that's the edge of one airy spot, coincides with the peak of the second airy spot. So it's like this. Okay? So they are barely resolvable from one another. Alright, that tells you the minimum angle of separation between these two stars would be the same as this angle, right? Because one comes this way, one comes that way, right? So this theta minimum really means what? It is the minimum angle separating the two stars that can be resolved with this lens. Okay, that is the resolution of the telescope. So a bigger telescope certainly does not only allow more light to go through, it also makes the resolution higher. And this formula is very useful. By the way, the Rayleigh criterion, you can also see it from here. I use different colors for that. This formula, you can forget about 1.22 if you just want to do a rough estimation. It's about lambda over d. This formula tells us that if everything else is the same, the bigger the eye of an animal, the more detailed the image the animal can see. Okay, now we can look at some examples. The human eye versus the eagle eye. Okay, eagles are predators in the sky, and in order to get what they want, they have to have sharper vision, right? They have to be able to see things very, from a far distance. In fact, they say an eagle can spot a small mouse on the ground from more than 1 mile away. Okay, now my question is, Is it really possible from what we learned about the minimum resolution? Okay, we know eagles have bigger eyes than most birds, and you can see that there is a reason for that, because you can gather light, even in the darkness better, and you can also see more detailed images, so you can actually find you find your prey more easily that way. Okay, so let's look at the human eye versus the eagle eye. Roughly speaking, the diameter of the human eye and the eagle eye are about of the order of 1 centimeter, I would say. Okay, 1 centimeter, and from that you can find out the minimum angular resolution. Okay, you find the minimum angle separating two objects that can be barely resolvable from an eye of diameter 1 centimeter. Let's look at let's do some numerical calculation, shall we? Okay, so you have theta minimum, so d is about 1 centimeter, and lambda, we use the center of the visible light spectrum. It's about 500 nanometers. 500 nanometers, and each nanometer, as you know, is 10 to negative 9 meters. So theta minimum, the minimum angle of resolution, would be about 500 nanometers divided by 1 centimeter. Okay, and you do that, you find the answer is about 5 times 10 to the negative 5 radian. Okay, so this is the smallest angle an eye of a diameter 1 centimeter can resolve. All right. Now, in the case of an eagle, okay, is it possible for an eagle to see a small mouse from a distance over a mile? Let's see here. If this is the size of an object on the ground, the eagle must resolve, and this is the distance between the object and the eagle. So the eagle is here. Okay, the eagle is here. And you want this angle theta to be less or equal to theta minimum, right? So you can actually see it. You can resolve it. Okay, in the case of a mouse, I would say the size would let's say small mouse, 10 centimeters. And this distance over a mile, let's say 2 kilometers, shall we? That's a little bit over a mile. The angle, 10 centimeters divided by 2 kilometers, what do you get? 10 centimeters over 2 kilometers. Guess what? The theta you get is about the same as this. It's about 5 times, you do this easy math, 10 times 10 to the negative 5 times 10 to the negative 5 radians. So yes, in principle, the eagle can see something as detailed as 10 centimeters apart from a mile away. Okay, so there is a reason why eagles need big eyes. And human eyes are not that different in size, but through evolution, the eagles have developed better eyes than us, because we don't really need to see things that well. We have other ways to get our prey. But eagles, they really have to rely on their eyes more than we do. Okay, what about something bigger? Something with a bigger diameter, say a big lens. Okay, let's look at the Hubble Space Telescope. The Hubble Space Telescope hovers about 400 kilometers above the Earth's surface, so that it doesn't have to get any distraction from the atmosphere of the Earth. And it's got a diameter about 2.5 meters. Okay, now, since the minimal angle that you can resolve is inversely proportional to the diameter, the resolution power is proportional to the diameter, and the Hubble Space Telescope is 250 centimeters in diameter. So it's got a resolution about 250 times as good as the human eye or the eagle eye. Okay, with that in mind, how well can the Hubble resolve things? Well, it's been said that if there are two flies a few meters away from each other, okay, here's fly 1, here's fly 2, the Hubble can see it from a distance that is equal to the diameter of the Earth. So here is the North Pole, and here's the South Pole, the distance between the Hubble and the two flies. And the two flies, even if they are flying only like 2 or 3 meters apart, the Hubble can still tell them apart. It can tell that these are two different flies. Okay, how is that possible? Now that is great resolution. How is that possible? Yes, it is, because look, theta minimum for the Hubble, you have to replace 1 centimeter with what? 2.5 meters, right? So theta minimum for the Hubble Space Telescope is roughly equal to 500 nanometers divided by nanometers. Okay, nanometers divided by 2.5 meters, right? And that is much better. That's 2 times 10 to the negative 7 radians. Okay, and you can do a little calculation. If the two flies are apart from each other by only about 3 meters, okay, only by 3 meters, and this distance between the two flies and the telescope is the diameter of the Earth. That's about 13,000 kilometers. This angle is still less than 2, it's still more, or slightly more, than 2 times 10 to the negative 7. So yes, indeed, the Hubble, in theory, can tell two flies apart, even if they're only separated by 3 meters, from a distance which is equal to the diameter of the Earth. That's how good it is. And if you aim the Hubble at the Moon, okay, this distance between the Earth and the Moon is 300,000 kilometers. Okay, this is expanded from 13,000 kilometers to 300,000 kilometers. And how far would 2 points on the Moon have to be in order for the Hubble to tell them apart? We can do this same estimation. Let this angle be theta minimum. Okay, and so you can find this distance. That's the minimum distance. The minimum distance. That 2 points will have to be apart for Hubble to see them at different points on the Moon. If you train Hubble directly at the Moon, you'll find that distance to be about 80 meters. About 80 meters. So indeed, when we look at images taken by Hubble of the Moon, we find a resolution about 80 meters. Okay, about 80 meters. And that is quite remarkable. Now imagine the same type of telescope with the same type of resolution. Looking down at the Earth from only 400 kilometers above the Earth, instead of looking at the Moon, so this distance is only 400 kilometers, you can certainly see things much better. Okay, you can see certainly much better. In fact, you will be able to resolve such details as the number of the information on the license plate number of a car, that sort of thing. So that's what the spy satellites. That's what they do. Okay, so what you need indeed is a big telescope with a large radius in order to have such fine resolution. All right.